In this section, we're talking about convolutional neural networks. So specifically, convolutional neural networks are any kind of neural network that has a convolutional layer. So all we really need to do to talk about convolutional networks is talk about convolutional layers. Convolutional layers work differently from any of the other kinds of layers that we've already discussed, though they have some properties in common with a max pooling layer. So I've drawn a picture here of how you might think about how a convolutional layer works. Up to this point, we've been working with the MNIST digits, which have 28 pixels width and 28 pixels height. So you can imagine that there was a digit drawn on the top of this, like a big number 2. Now, this is a 3-dimensional box. The MNIST digits only had darkness. They were monochromatic, black and white images. However, we're about to start working with full color images. And color images have 3 spectrums of color. So we now have 3 layers of depth to any kind of input image. Later on in this lesson, we'll be using the Oxford Flower database to train on. And so in addition to each flower picture having a width and a height, we'll also have a depth of 3 to represent color. So that's one little thing that we need to talk about. Now we can actually talk about what the convolutional layer does. So what it does is similar to the way that the max pooling layer slid over the surface of our larger image. So does a convolutional layer. So it has this patch or this sliding window. I've decided here that it has a 3 pixel by 3 pixel height and width. It always has the depth 3 as well. And it passes at some stride length, and we could have stride length of 2 or 3, and that means that we pass at even increments across the image. And the interesting thing here is with the max pooling layer, it was pretty easy to think about, okay, well, we had, these 2 or 3 pixel squares, and we're compressing those into some smaller image. Convolutional networks are quite different from that in that this 3 by 3 sliding window over all of the image starts to represent a single type of aspect of the image. So if there was some kind of corner, like the bottom of a number 2, then regardless of where it is in the image, a single neuron in a convolutional layer will start to represent that edge. So any kind of 3 by 3 pixel edge that fits in will be noticed anywhere in this image. So convolutional layers lose the sense of location. So all of a sudden, a single neuron in the convolutional layer represents any kind of shape or a particular kind of shape anywhere in the image. So this is a powerful thing. It's way more efficient than a dense network, which has these huge, fully connected mappings. Instead, we're trying to represent a discrete thing with location invariance in this single neuron. It's a very powerful concept, and the name convolution is related to the mathematical operation called a convolution that allows this sliding window to pass over the image or the input. Now, the other parameter that we've talked about here, so we've talked about the width and the height, so this 3 by 3 size of the patch or the sliding window, which we can call the kernel size. We haven't talked about the number of neurons. So the language here can be a bit confusing because some people will call this neurons, they'll call them kernels, they'll call them filters. So every single one of these location invariant representations is stored within a neuron, and we need to decide ourselves as we create the network what size or how many neurons we want to have, how many neurons or kernels or filters we want to have. So in the first network that we build, one of our first convolutional layer will have 32 neurons. So then we have 32 discrete representations of 3 by 3 things that can happen anywhere on this entire image. And later on we'll have one with 64. Squares of 2 tend to be common in this kind of layer.